Our next speaker is the distinguished faculty from the Department of Mechanical Engineering, Professor Ghanem Oweis. Dr. Oweis received his PhD from the University of Michigan, his master's from the University of Leeds, and his bachelor from Jordan. He is currently an associate professor at the Department of Mechanical Engineering, and he has received several awards for his research work, including Abdul Hamid Hallab REP Service Excellence Award in 2007, and received the Medal of the Lebanese Electric Utility in 2007 as well. Dr. Ghanem, okay. Well, his research interests and teaching interests are in fluid mechanics and thermal sciences. Please join me in welcoming Dr. Ghanem Oweis.
Hey, good afternoon. Thank you very much for this nice introduction. Can't see the presentation here for some reason. And thank you everyone for showing up on this afternoon. It's getting warm in here. So while Matthias is putting this up, if you take a piece of paper and try and do this, it's hot, right? So do this and you can feel something. But can you see the air that's moving around? Probably not. If you can see it, then you have special abilities. So let's see. Why would you be interested in seeing the air that's moving around when you do this? Well, because birds do it. And, oops. Okay, so this is the laser, cool. So birds do it, and as engineers and as humans, we are interested in flight. We want to fly. And Leonardo da Vinci has drawn this 500 years ago or more. He was interested in this same topic. And if you see what he said if you want to learn how birds fly, you really need to know or understand how the wind moves around the wing. So this was a 500-year wisdom that is still true today. And he said, well, we can't see the air, so what do you do? So his solution was to let's go look at water. Water is easier to look at and see than the air, because you can look outside the window, you'll see the water in the sea, but not the air that's here. Okay, so the picture is not very clear, but if you take my word for it, there's a human being here, drawn by Leonardo, and trying to operate a flap, a couple of wings. So it's one of the earlier designs for a flying machine. And right there, if you also believe me, there is the detailed design of the wing. So you still, well, we can't see anything, right? So he did this, and then he decided that, well, for me to be able to understand how my wing design works, I need to be able to see the details. And to be able to see the details, he decided to go and look at water. So he brought a couple of obstacles. So these are rectangles. And he set them at different angles to the incoming flow. And this 15th century technology, with it you can see the flow come, bend around. You can see the wakes behind the plate. You can see the growth rate of the wake. You can see the details of the turbulence, which is something that we even cherish today because it's very high tech even today to be able to capture all that level of details with just his eyes and his hands too. I mean, you can see it and think about it, but to be able to jot it on a piece of paper is something else. So this was the technology. So you really need special abilities to be able to do this, like Leonardo da Vinci. So nothing happened for the next 500 years until lasers and cameras came. So now I can see the air in this room, not now, but if I bring my camera and lasers. So imagine that this is the piece of paper that did this with it, and I want to look at the flow around it. So this is my flow region, and if I want to know what are the details of the flow that happen in there, what I'll do is I'll get a laser beam, just like the one that I have in my finger, and I'll put it through a lens, and we'll expand it. It becomes a light sheet. And then we'll get some smoke or some dust particles. So now it was dusty a couple of weeks ago. And you see the flow. And then you look at them with a camera. So now how the details of the laser, you can flash it, you can be continuous laser, the camera can be fast, it can be slow. And then what you do is you get pictures like this. I hope you can see part of it because it's a really nice picture taken in AUV's wind tunnel. And in it, what you see is the flow is coming from left to right. So this is a wind tunnel. Here is a cylinder. And you can see, it's hard actually to see, but the wake is visible. The bending around of the flow around the cylinder is right here, is obvious. And there are so many levels of details in the wake structure that are actually comparable to what Leonardo da Vinci was able to see and jot down 500 years ago or more. So this is qualitative. We can still do more. There's nothing you can see here, but if you take my word for it, you can zoom in and reduce the amount of flow seeding, and you can actually see sort of individual particles. And if you take multiple frames of these individual particles with time, so you take sequence and time like a video, you can actually correlate them. So that's also this is a cylinder here. The flow is going from left to right. The laser illuminates the particles, so we can see them with the camera. And now we can sort of see individual particles or identify groups of particles. And then if I have two or more of this picture, I can create a wind map of what's really happening behind this cylinder that's sitting in the wind tunnel, which is also the same thing if what happens behind this flapping piece of paper that's in my hand. And you can tell a lot of the details that happen. So this cylinder is about, 7-8 centimeters in diameter. So you can get a scale of the details of the flow that occur over here. So it looks like the weather map that you see in the nightly news. And this is the technology that we currently have and that I work with. And what I'd like to show you next, now that I've explained this, I'd like to show you two examples of what we have done using flow visualization, or being able to see the light, or being able to see the flow using light, so optical imaging. The first one would be the flow around a cactus tree. So if you look at those trees, they're amazing because the scale is amazing. You can see a person for a scale, and they're large in size, and their engineering marvel is that they don't have a strong rooting system, and they're very tall, they're very large in diameter, so they can topple very easily. But they don't. And the toppling mechanism the loading on these kinds of trees is primarily the wind. And they can negotiate the wind very well. They don't bend, but they survive the wind in a very remarkable fashion. And that's because they have these kinds of surface grooves. So unlike round circular trunks, these trees have star-shaped cross-sections. And so we set out to understand why these trees, what are the wind mechanisms, flow mechanisms that make these geometries, the star-shaped geometry, resistant to wind toppling. So again, in our wind tunnel, we built a cactus model, which is what you see, shine a laser on it, We throw some smoke with the incoming stream. We look at it with a camera. And we compare a circular cylinder with a cactus-shaped cylinder. And again, believe me, that here we're showing contours of turbulence intensities. That so the red is more turbulent. For the circular cylinders here, the cactus cylinders here. The turbulence intensities for the cactus cylinder in the wake are actually significantly less or smaller than the circular cylinder or a round trunk. So that's a result. And then we set out to know why, and you'd expect it would be the grooves. So we look at the flow around the groove. So the flow is coming from right to left as the arrow points, and we're looking at the groove flow. And these spikes or mountains in the cactus geometry shed vortices, because here we're looking at vorticity, and they make the flow nicely behaved and well attached. And there are engineering applications. For instance, you look at the Burj Dubai, it has features borrowed from the cactus tree. So the second application, I'll go really quick, where we're using light to look at transparent material. I'm looking at safe. To look at transparent material is ultrasonic ablation of cancer tumors. So what you have here is an ultrasonic transducer placed outside the body, and it's geometrically focused. So the white lines are the ultrasound beams, and you can see they're geometrically focused onto a point, and then they open up. So this is targeted. So it's targeted on a specific area. And if you put enough energy at the transducer, you can ablate a region inside the body. So the transducer, as I said, is outside the skin of the patient, while the tumor or the mass you're trying to ablate is inside the patient. Could be the liver, it could be the kidney. And the sound waves do something here. So if you put enough energy, you can heat the material, and you can cook it, and you can do other things like cavitation, as well as hyperthermia, so just raising the temperature slightly to prepare the material, to prepare the patient for another kind of treatment, so in a synergetic effect. So for the safety and efficacy of such kind of treatment, you really need to know what's happening in here. So we're using the same tools and techniques that we used with the cactus tree to be able to look at the sound waves, the pressure, temperature, and so on. So we built a small system in the lab. It's on the 3rd floor. You're welcome to visit if you like, down here in the same building, 319. So what you have is, this is the HIFU device that we have. It's the ultrasonic device. We have a tissue-mimicking phantom. The ultrasonic device focuses energy onto the tissue-mimicking phantom. And it causes the effect of heating, sound wave, sound pressure, and so on. And a laser probes the region, so it illuminates the tissue-mimicking phantom, and it illuminates the sound waves. And we look at it with a camera from where you're sitting. So believe me here again, that you can actually see the sound waves. I should have made this presentation in the morning when the sun is not shining as from the west. But we can see the sound waves. There's actually a better picture here. So this is what, this is called the acoustic particle velocity. When I'm speaking, I'm shaking the air particles in their place. And I can actually see that shaking of the particles at the HIFU. The HIFU is the transducer, the high-intensity focused ultrasound transducer. So we can see what's really happening in there, and I can convert this into pressure field, which is the essential piece of information that we were after. And then could use that same technique also to, if this is my ultrasonic transducer, this is the tissue-mimicking phantom, that's the heated spot, I can use my laser techniques to look at the temperature at multiple locations or in the heated region. So this is, so I hope I made it in time. My conclusions would be really, if you're interested, we are looking for students. So come and talk to me afterwards. You're welcome. So thank you.
Thank you, Dr. Oweis.